All right, we're going to hop into chapter 6, which is called Hypothesis Tests with Means of Samples. And I kind of gave you a forewarning last chapter that this chapter was going to be the same, but there's going to be a complex idea that we have to kind of unravel. And I think that if you remember to breathe and hang in there, that you'll be able to pick it up. There's a very basic piece of logic that you really have to grasp onto, and once you do that, it makes things a lot easier. Whatever you do, don't panic, it's not that bad. So in chapter 6, the big deal is that we are going to compare the mean of one distribution to a known population of individuals. Okay, so let me just kind of give you a quick for instance. For instance, let's say that we think that people at Olivet College, called the population, they like the KC food, maybe a 5 out of 10. And let's say that we have a social science statistics class that likes the KC food 7 out of 10. We can conduct a hypothesis test in order to determine if there is a significant difference between Olivet College students in general and the people in this class in terms of how much they like KC food. Now, the difference between this chapter and last chapter is that rather than comparing one individual person to a population to see if their score is significantly different, what we are doing in this chapter is comparing the mean of a group to the mean of a population of individual scores. There is a little hiccup that we have to work through, and that's what creates all the mess in this chapter. But don't worry, we're going to be able to work through it. And once we start to work through a couple examples, just real linearly, just from step 1 through step 5, I think you're going to pick it up. But in the meantime, we have to look at a couple of basic ideas in how we do steps 1 through 5. And the good news is that there aren't a lot of changes to steps 1, 3, and 5. So let's go ahead and frame our example for this chapter, and then we will jump into kind of the nitty-gritty stuff. So the chapter that we're going to be working with is this. Educational psychologists wonder if special instructions on an achievement test will yield higher scores if there are no special instructions. So it sounds like we have two groups already. One group is going to get special instructions on how to complete a test, and the other group is not given special instructions. A group of 64 juniors, so our n is equal to 64, that sounds like our sample, is given special instructions to select the first item that comes to mind. So when they look at the question, they just select the first answer that comes to mind and move on. Other students are not given that instruction, probably assuming that they will think about it and use some kind of cognitive strategy in order to solve the question. In this example, the other students who were not given special instructions had a mean of 200 with a standard deviation of 48. So whatever this test is, it has a range from 0 to 400. Maybe there are 400 questions and it's just how many questions you got right. Whatever it is, they had a mean of 200 and a standard deviation of 48. So mu, the population mean, is equal to 200. And lowercase sigma is equal to 48, or the population standard deviation is 48. So the group that we're going to compare our sample to had a mean of 200, a standard deviation of 48. We're going to look into that a little bit later, but let's just set up the example for now. The students that were given special instructions had a mean score of 220, so the mean equaled 220. So the sample mean was equal to 220, so there was a 20-point increase on their test scores, but we need to know if that is significantly different or not, and we'll take a look at that. We're going to use a conventional p is less than 0.05 cutoff to make a decision on whether or not there is a significant increase in the group of 64. There's our example. I think that we can kind of wrap our heads around it. We're going to come back to that. The difference between a z-test with a single score and the mean of many scores is that we need to determine what our new comparison distribution will be. When we worked with a single score, a sample of one individual, like in the last chapter, and we compared that to a population of individual scores, it was a very easy comparison to determine if that single score was significantly different than a bunch of other single scores. In this chapter, we're going to look at the mean of many scores, 64 in the example that we're working with, and we need to compare that to a distribution of individual scores. There's a big problem with that, though. The law of averages says that when we have a mean of many scores, that mean is less likely to be further from the actual population mean. So if we have a sample of 64 scores, the mean that we get from those 64 scores is not likely to vary from the population mean by very much, as opposed to one score, which could have a decent chance of varying from the population mean. I'll say that again, maybe in a different way. If we had an individual from a population, so if we had many people, and we took one score from that, we know that there is a 5% chance that that person would be significant, because we usually say that if a person is in the 5% most extreme scores, then they are significant. If we had one individual, we'd have a 5% chance of pulling that person from the extreme score. Now, if we had the average of 64 scores, we would be very unlikely for that average to find itself in the 5% most extreme scores based on our population. Because if we had 64 scores, they would all have to be very extreme in order for those 64 scores to average a score that would be extreme enough to be in the top 5% of all the scores. Undoubtedly, some of those scores would be very low if we took 64 people randomly. Some of them would be very high, but it'd be very seldom a case where the average of those 64 scores would be so extreme that they would be significant on average. In short, it's unfair to compare the mean of a group to a distribution of individual scores. We have to do something in order to make that a fair comparison. So we need to address the population, which is this. So in our example, there is a group of juniors who took the achievement test with no other instructions except for to simply answer any way they would like to. That's the population. And on average, the group of juniors scored a 200 on a 0 to 400 scale. The standard deviation of that group was 48. Okay, we have a mean of 0 and a standard deviation of +1, +2, -1, -2. Even though we don't need to, we could put the raw scores on here. That would be fine. So if we know that the population mean was 200, then we can go ahead and put that here. 200 is the population mean. If we know that the population standard deviation was equal to 48, we can put that on here too. So it's 248 and 296, and then going backwards, 152, and then 104. So this is our raw scale. We can call that our X scale because that's the raw scale. So we have a standard deviation of 48, population mean of 200. So our sample distribution is the score of the 64 individuals who were given special instructions. We know that there were 64 scores there, but we'll talk about the mean and standard deviation of those 64 scores just a little bit later. Now, last chapter we compared an individual score with the distribution of individual scores, and it looked kind of like this, where we had our two-tailed cutoff, and then we had one individual score that fell somewhere, and we could determine if that score were significant or non-significant. In this particular graphic, it's non-significant because it does not fall in either of the rejection zones. In this chapter, we're comparing the mean of one group to a distribution of individual scores. So let's say that population 2, which is our population, is equal to infinity. It has many scores. It doesn't matter how many, just theoretically infinite. Population 1, in our case, is our sample, and it has 64 scores. I just kind of put a curve. This may not be exactly where our sample is, but this is just a for instance. In order for our mean to be significant, In other words, in order for this distribution of our 64 scores, in order for that to be significant, this mean must be in our rejection zone. So for example, there are some scores that are significant. There are some scores from that mean or from that distribution that are significant because some of this distribution has scores that fall in the rejection zone. However, the average or the mean does not. So even though we had some scores that were significant, the overall mean or the overall distribution is non-significant. As a matter of fact, we could have 49% of all these scores. So every score just to the right of the mean could be in that rejection zone. So we could take, maybe I can take that. If I move this over to right there, that would be an interesting finding, but it would not be significant because the mean of these scores must be entirely in the rejection zone. Now, if we take a look at this from another perspective, look at how many scores are significant and look way out here. These scores would be, looks like 1, 2, 3, maybe even close to 4 standard deviations above the mean. But because you have these other scores, because the majority of the scores are not significant, we have a non-significant result. Now, would this be close? Sure. But is it significant? No, it's not. In order for our result to be significant, the sample mean must be entirely in the rejection zone. And as you can see, that could be very hard to do if we compared it just to a regular distribution from the population. The problem is this: we cannot compare the mean of a group of scores to a distribution of individual scores. The central limit theorem or the law of averages states that the larger the group is, the less spread the group's scores are. So if we have a mean of 64 scores, that distribution's mean is not likely to vary from the population by very much, just based on averages. And the more people you get in the sample, the less likely it is to vary from the mean of that distribution. We went over the logic in the last slide. Maybe I got ahead of myself. But the idea, again, is that some of these scores will be in the rejection zone, but if the mean is not, then we are not able to consider it to be significant. I took some actual data, and really it's just a random number generator. So what I have here is a histogram of 1,000 scores. And as you can see, I put a normal curve over the histogram to kind of show you where the normal curve would fall on this. And the data pretty much follows the normal curve. Pardon the fact that there's a label that I've kind of plastered this scale over, but that's okay. So let's say that we have 1,000 scores with a mean of 50 and a standard deviation of 15. It's just an example. It doesn't matter what the mean and standard deviation are, really. It's just a for instance. Now, let's say that we had this population of individual scores and we wanted to take a sample and see if that sample was significantly different than this population, our comparison distribution. Now, it doesn't matter what it is, but let's say that we just use this comparison distribution. We would need a cutoff z-score equal to positive 1.64 because we know that a cutoff z-score on a one-tailed test positive is 1.64. We would need to see a raw score of 74.6 in our mean. So if we wanted to, let's say, take 64 of these scores, it doesn't matter how many, if we wanted to take 64 of these scores randomly, and maybe we had them answer a question, but we give them a little more information and they could answer it differently. Let's say it's something like, how much do you like being at Olivet College? And we just had, 1,000 people answer the question, and we took 64 people and we said, how do you like Olivet College, knowing that I'm going to pay you $25 for participating? Because we're paying to participate, which is an interesting phenomenon, by the way, people would be more willing to rate something higher just because they're getting paid, even though their idea of Olivet College stays the same. So when you think about how you compensate people for participation in a survey, remember, you're going to automatically get higher scores just because you compensate somebody. Whatever. It's interesting, but inconsequential to this example. So we give them $100, let's say, or $25 or $5, whatever it is, and we say, how do you like Olivet College? And they say, oh, well, I like Olivet College quite a bit. So on average, that sample has a mean of 62, which would be very significant, by the way. But because we're comparing it to this distribution of individual scores, a strong increase from 50 to 62 would still not be significant. Look at that. A 62 is barely outside of 1 standard deviation according to the population. It's certainly nowhere in this rejection zone. We need to figure out a way to make this comparison distribution more fair. That is, we need to figure out a way to take this distribution of individual scores, and rather than make it a distribution of individual scores, make it a distribution of the means of 64 scores. Because if we're working with a sample size of 64, we should be comparing a sample size of 64 to a distribution that's based on a sample size of 64. Now, I'm going to demonstrate this for you to kind of give you a visualization of what I'm talking about, because this might seem very nebulous, like, okay, I hear you saying lots of words, and they may even be in the right order, but it doesn't make sense to me. The good news for us, though, is that we only have to make a change to step 2 and kind of a change in step 4-ish, just with the formula. When we are going to create what's called a distribution of means, and we'll see why it's called that in a moment, we need to adjust the population distribution, also called the comparison distribution, in order to do that. So really, it's a change in step number 2, which leads to a small change in step number 4 just because of the formula. We just use different symbols. We can convert that distribution of individual scores to a distribution that looks more like the sample. And it's all done theoretically because we're modifying a population of usually an unknown number. So I'm going to give you a visualization of what that looks like. I'll give you 2 types of visualizations of how that looks actually. And then we'll take a look at how we do it just with a simple set of formulas. Now, the distribution of means is based on this idea. We have a population of individual scores. This is our distribution, let's say, of 1,000 people at Olivet College, or from our example, students who took a test with no special instructions. Whatever it is, it's our population. It's the group that we are comparing our sample to. We take our population of individual scores. We're going to randomly take some number of scores that's equal to the sample size. So in the examples we've been using, it's been 64, but just for the sake of demonstrating what it looks like, let's say we took 5 people, or 5 scores from this group of individual scores. We took the mean of those 5 scores, and then we plotted them on a new histogram. Then we did it again, where we took 5 more random scores, we took their means, and then we plotted that on a new histogram. And we did it again, and again, and again, and again, theoretically an infinite amount of times. But what would end up happening is that we would take 5 scores, and we would take the mean of those 5 scores and plot them on a new distribution. We would end up getting a distribution that has exactly the same mean as the population, but the spread of that distribution would be much, much more narrow. Be much, much more narrow. As a matter of fact, if we took 5 scores, the distribution would get very narrow. If we took the mean of 64 scores multiple times, this would become even more narrow. In this demonstration, it kind of shows you what that might look like. If we had a sample size of 1, which is kind of just like saying if we had a bunch of individual scores, we would have a normal curve. If we took 10 scores from the population, averaged them many times, we would get a narrow distribution. If we took 100 scores from the population, took the mean of those 100 scores, did that many, many times, we'd have an incredibly narrow distribution of scores. Eventually what would happen, and this is actually from the example that we're using in this chapter about the test-taking strategies among the juniors, we would go from a distribution of individual scores that has a mean of 200 and a standard deviation of 48 to a population comparison distribution that's called the distribution of means that has a mean of 200 and a standard deviation that's much, much narrower. We'll take a look at what that is exactly. But let's go ahead and stop right here. I want to run through a demonstration of how the distribution of means is created using a visual representation. In this demonstration, we are going to take a look at how to create distributions of means from a physical perspective. We're actually going to see it happen. We have a population that has a mean of 50 and a standard deviation of 16. For the sake of this example, let's say that we have 64 people that we have in a sample that we want to compare the mean to. So we want to compare the mean of our 64 people to a population of many, many, many people. And the population of individual scores has a mean of 50, a standard deviation equal to 16. You can kind of see the scale up top here. What's going to happen is that we are going to take a sample of 64 people from this population, we're going to find their mean, and we're going to plot it down here on a new distribution. What we are doing is we are taking our distribution of individual scores, which is our comparison distribution, and because we have a sample of 64 that we want to compare to our group of individual scores from the population, we need to create a distribution of scores that is the mean of 64 of these scores averaged to, or well, it is average because it's the mean, but plotted on a new histogram that demonstrates our distribution of means with a similar mean but a narrower spread of scores that will more likely match the spread of scores from our sample. That is, if we take the mean of 64 scores, they are less likely to be spread from the actual population mean because of the law of averages. So let's take a look at that. As you can see, what is happening is you have the blue dots, which are representative of 64 individual scores, and those blue dots are being averaged by the green dots. The green dots represent the average of all the blue dots, and those are going to fall down into a new distribution. It's just a graphical way of seeing how it happens. And eventually this new distribution is going to start to develop a shape. And as you see the shape, it'll represent what is called the distribution of means. Let's watch it. And as we watch it, it begins to grow and grow and grow. And you can see that this sample of 64 scores never really varies from the mean by, it's not even more than one standard deviation. So as you can see, the spread of scores becomes very narrow, meaning that on this new distribution, if we have a z-score that is around positive 1.64, for example, in the case of a one-tailed or a z-test, you can see that now the scores are more likely to be significant. That is, our sample scores are more likely to be significant because of how much closer to the actual mean our cutoff is. And as we stop, we can see that there is a good tall peak with a very narrow spread of scores, and this will be a better comparison distribution to compare our sample to. This is the logic and the visualization of what the distribution of means looks like. This is how it is done. We will use a simple formula in order to replicate this, but as you can see, the mean stays the same, but the spread of scores becomes very, very small, as indicated by the mean heaps standard deviation, which is it's identified by what's called the curve SE. Don't worry about the terminology, it's the same thing. But the curve standard error is the same thing as the standard deviation of the distribution of means. You can see how much smaller it gets. So as you can see, when we have a population distribution and we create a distribution of means or a sampling distribution of the mean, it becomes very narrow. And this better represents the sample's comparison distribution because the sample is based on the mean of 64 scores. Step 2 is really the only step that's effective, even though step number 4 kind of does have a small change to it. In step number 2, we need to define the characteristics of the comparison distribution. But we need to create a distribution of means that's based on our comparison distribution. So we need to create a distribution of means of 64 scores. This allows us to compare the mean of our sample of 64 to a distribution of scores that is also the average or the mean of 64 scores, but taken many, many, many times. In order to do that, we use a set of formulas that are fairly simple to use. So in step number 2, we're going to describe the characteristics of the comparison distribution. The original distribution is of individual scores. So in the example that we're working in the chapter, the distribution of individual scores is just a distribution of the juniors that were taking the test without any special instructions. It's just a bunch of individual scores that have a mean and a standard deviation. In order to convert this distribution of individual scores to a new distribution that is the mean of 64 scores taken many times, we can use a few formulas that are pretty easy. Now, we know that the rule is that the mean of the distribution of individual scores is equal to the mean of the distribution of means. So the mean of the individual scores is equal to the mean of the distribution of means. The variance of the distribution of means is equal to the variance of the population divided by the number in each sample. So in order to do this, we find out how spread out the scores are by looking at the variance and dividing it by the number in each sample, and that makes that spread of scores much smaller. Then once we have the variance of the distribution of means, we can find the standard deviation of the distribution of means by taking the square root of what we found in the second rule. So we take the square root of the variance, just like we did when we did standard deviation from chapter 2. We take the square root of the variance, or the square root of the variance of the distribution of means, or the square root of the variance of the population divided by n, which is the same thing, right? Because on one side of the equation, we have the variance of the population divided by n. On the other side, we have let me start that over. On one side, we have the variance of the population divided by n, and on the other side, we have the variance of the distribution of means. So those are equal, so we know that we can take the square root of either of those and we're good to go. And if we plug some numbers into that, we can move forward with our example. So let's say that we are working from the example in the book and we have a population mean of 200, a population standard deviation of 48, and there are 64 people in our sample. So we're going to compare the mean of 64 people. We haven't gotten to what the actual mean is yet, but we'll get to that in a second. So the sample of 64 people has a mean that we're going to compare to our population. So our population mean is 200, standard deviation of 48, which is replicated on the curve here. The rule for creating the distribution of means is pretty straightforward. The mean of the distribution of means is equal to the mean of the population, which is equal to 200. So we can plot the mean of our distribution of means. The variance of the distribution of means is equal to the variance of the population divided by n. So we're going to take our population variance, which is pretty wide. This is a standard deviation down here, but it's still indicated as such. So the population variance divided by n is equal to, wait a second, 48. I thought that was the standard deviation. Well, it is. In order to get variance from the standard deviation, we square it. And vice versa. Whenever we want to get the standard deviation from the variance, we take the square root. So if we square the standard deviation, we get the variance. So 48 squared divided by 64 is equal to 2,304 divided by 64, which is equal to 36. That is our population variance of the distribution of means. In order to get the standard deviation of the distribution of means, we can take the square root of the variance of the distribution of means, or we could take the square root of the variance of the population divided by n. So standard deviation of the distribution of means is equal to the square root of the variance of the distribution of means, or the square root of the variance of the population divided by n, which is equal to the square root of 36, which is equal to 6. So our new comparison distribution, which is the distribution of means, has a mean equal to 200 and a standard deviation of 6, which is indicated here. And pardon that all the numbers are squashed together as a very narrow curve. Let's move into our example now that we've kind of trudged through some of the logic and visualization. of the distribution of means and get into something that we can probably sink our teeth into. So here's a refresher for our example that we've been kind of dancing around now. Educational psychologists wonder if special instructions on an achievement test will yield higher scores than if there are no special instructions. A group of 64 juniors, n equals 64, is given special instructions to select the first item that comes to mind. Other students are not given that instruction. In this example, the other students who were not given special instructions had a mean of 200 with a standard deviation of 48. That is our population. That's our comparison distribution. The mean of the population is equal to 200, standard deviation of 48. We're going to go through step 2 in a second, which is why you don't see anything about the distribution of means, but we'll get there. The students who were given special instructions had a mean of 220. We will use a p is less than 0.05 cutoff, which is also the same thing as saying alpha equal to 0.05, to make a decision on whether or not there is a significant increase in the group of 64 people in the sample. Step number 1. We need to restate the research questions as a research hypothesis and a null hypothesis and identify the populations or the groups. The research question is there a significant increase in the test scores for the students who received special instructions compared to those who did not? Population 1 is the students who get special instructions, and population 2 are the high school students in general, the high school juniors in general, those who did not get the special instructions. The research hypothesis is that population 1 scores will be significantly greater than population 2 scores, or population 1, which is our sample mean, will be greater than population 2, which is our population mean. The null hypothesis, which is true if there is no significant difference, is that population 1 scores will not be significantly greater than population 2 scores, or that population 1, which is the mean of the sample, will be less than or equal to population 2, which is the mean of the population. Step number 2. Now, before we jump right into it, I just want to kind of bring something forward here. And I'm going to enter the population mean. This is the mean of the individuals who were in the sample, who we are comparing to the population. This distribution of individual scores is based on the population. Now, let's say for just a second that we took the mean of 64 scores, which in this case is 220, and just compared it to a distribution of individual scores. The mean of those 64 scores is 220, which is approximately in this area. Now, clearly, 220 is not a score that's going to be extreme enough compared to the comparison distribution to be significant. That is the battle that we're fighting when we have to compare the mean of 64 scores, for example, to a distribution of individual scores, which is why we create our distribution of means. Now, we're going to apply our rules again. This will be review. We've already done this, but I want to do it linear. So the rules for creating the distribution of means is to take the mean of the population, which is 200, and that equals the mean of our distribution of means. The standard deviation of the distribution, let me start that over. The variance of the distribution of means is equal to the variance of the population divided by n, which is equal to 48 squared, because remember we square our standard deviation to get variance, divided by 64 equals 2,304 divided by 64, which equals 36. So the variance of the distribution of means equals 36. The standard deviation of the distribution of means is equal to the square root of the variance of the distribution of means, or the square root of the variance of the population divided by n, which is equal to 36, which is equal to 6. So we have a comparison distribution that now has a mean of 200 and a standard deviation equal to 6. So it looks like this. Step 3 is largely the same, but the difference is that we're going to use the distribution of means as our comparison distribution. So step 3, we need to determine the cutoff score on the comparison distribution. We're going to use an alpha level of p is less than 0.05, or alpha level equals 0.05. The direction, one-tailed or two-tailed, well, we haven't really talked about that. If I go back to the example, We want to know if special instructions on an achievement test will yield higher scores than if there are no instructions. So it sounds like, based on the language that I see, that we are looking for a greater score, which means that it is a one-tailed test in the positive direction. We are concerned about a positive change. So we're going to use a one-tailed test. In order to find the cutoff z-score for a one-tailed test at the 0.05 alpha level, we can consult our z-table, or we can use the cheat sheet that we got in chapter number 5. So the cutoff z-score, which is our alpha, is equal to positive 1.64, which means that if our sample's z-score, so if the mean of our sample has a z-score that is greater than 1.64, then we will reject the null hypothesis, and that's based on our comparison distribution, which is now a distribution of means. So rather than using our distribution of individual scores here, and imagine if we had a cutoff z-score of positive 1.64 here, our sample would have had to have had a mean of somewhere in the neighborhood of 270 or so. But rather than that, the cutoff z-score is in the neighborhood of 208 or 9 or 10 or somewhere in there. Let's take a look at step number 4. Step number 4 is to determine the sample score on the comparison distribution. We need to find out where our sample's z-score is. The sample z-score is equal to the mean of the sample minus the population mean, or in this case, which is the mean of the distribution of means, divided by the standard deviation of the distribution of means. In step number 2, we determine the characteristics, and we determine that the sample mean is 220, and that was really given to us in the example. The population mean, which is the mean of the distribution of means, is equal to 200, and the standard deviation of the distribution of means is 6. So 220 minus 200 divided by 6 is equal to 20 divided by 6 is equal to 3.33. Our sample's z-score. So if you had a score of 220 on our comparison distribution, the z-score would equal 3.33, meaning that our sample's z-score is 3.33 standard deviations above the mean. Let's take a look at that graphically in step number 5. Step number 5, we have this 3.33 line, which is 1, 2, 3 is not represented, but it's approximately there, and 3 standard deviations above the mean. That's where our sample mean is. So more accurately, this would have a normal curve around it. Let me put that in there real quick. There, that's a little bit better. So we have our sample's mean of 220 is approximately 3.33 standard deviations above the mean. So if we look at this just graphically, wow, it looks like it's significant, but let's go ahead and bring forward our null hypothesis so we can determine if our z-score is significant. So when we bring forward our null hypothesis, we're talking about two populations, our sample, which is the first population, and the comparison distribution, which is population 2. So we want to know if our sample is less than or equal to the comparison distribution or the population 2 z-score. We do that in terms of z-scores. So the sample z-score is 3.33. And when we talk about our population 2 z-score, we're talking about our cutoff z-score, which is positive 1.64. Now, this is the null hypothesis. We need to make a decision about the null hypothesis by rejecting it or failing to reject it. So in this particular case, our sample z-score is 3.33. The population cutoff is 1.64, or our cutoff z-score is 1.64. Is 3.33 less than or equal to 1.64? The answer to that is no. 3.33 is not less than 1.64. So we reject this statement, which means that we reject the null hypothesis. The null hypothesis is what is true if there is not a significant difference between the two scores, so we reject the null hypothesis. When we reject the null hypothesis, what we are saying is that there is a significant difference, or if we say it very inside out, we are rejecting the idea that our sample score is less than or equal to our cutoff score. When we look at the result statement, it is a narrative, and this is a good primer for going forward in chapters 8 and so on, because we are going to be talking about how we create a results section. So this is just a good way to prime you into thinking about how we conclude a statistical test. A z-test was conducted to determine if there was a significant increase in test scores between the sample mean of juniors who received special instructions, mean is equal to 220, n is equal to 64, and the juniors who received no special instructions, population mean is equal to 200, standard deviation equal to 48. There was a significant increase in the mean of the sample compared to the comparison distribution's cutoff z-score. Z of the sample was equal to 3.33. The cutoff z-score, or z of the cutoff, is equal to 1.64. These results indicate that there is a significant increase in test scores when special instructions are given to the junior students. Now, even though this chapter seems complicated, you can always kind of zoom back out and recognize that all we're doing is comparing the mean of one distribution to a known population of individuals. We have to do a little bit of dancing around the comparison distribution in order to make it fair, but I think that once you understand the basic logic, you'll be able to apply these steps fairly easily. Now, even if you don't understand the logic 100%, you can still walk through the mechanics of each step and arrive at the right conclusion. As long as you do everything at steps 1 through 4 correctly, you can make the decision in step 5 and come to the correct conclusion. I do hope that you're able to pick up and understand the logic and the sentiment of doing the distribution of means, but if you didn't, you would still be able to do statistical analysis with z-test and going forward in the t-test, f-test, etc. Without having to have the perfect understanding of it. Again, I hope that you do, and I hope that you're able to kind of understand the basic idea, but please don't stress and panic if you aren't able to articulate this exactly. So that is chapter number 6, the last chapter before the exam. I'll give you a hint. If you can do steps 1 through 5 in the example that we did and kind of follow it along and be able to input things mechanically and make decisions about step number 5, you're going to be in really good shape for the exam. So I look forward to seeing what you can do.